Welcome to Pirtek Learn and Development. Today we'll be looking at tube bending, tube assemblies, and flaring tubes. The hose assembly and installation and the training reference guide will be used in this lecture. Learner guides, references, all available for download from Moodle. Don't forget, Connect is another great resource. The fittings catalogue that's referenced in this lecture was downloaded from www.pirtek.com.au. In today's lecture, we'll be looking at tube benders and bending, tube fittings and preparation, and flaring tubes. Tube benders and bending. There is a vast variety of tube benders on the market, cheap generic units and quality units. Irrespective of the quality, it's important to determine the maximum tube size, the bend radius, and if it's capable of bending your particular material. Check with the operators or user's manual that come with the tube bender. Most benders will come stamped with a maximum tube diameter and bend radius. These dimensions are important because we use them to calculate the bend allowance. Here's an example of bend allowance. The overall length of the tube is 200 millimeters, but when we bend it 90 degrees in the center, it becomes shorter at one end. We need to be able to predict this shortfall and add it to the length of the tube before we start bending. What information do we need to calculate the bending allowance? We'll need the radius of the tube bender, which is usually stamped on the unit or in the instruction manual, and the diameter of the tube that we're bending. We can calculate the bending allowance using lookup charts, Machinery's Handbook, for example, or the instruction manual that came with the bender, or we can use a simple mathematical formula, and that's what we'll be doing today. The formula. Let's have a look at the formula in general. We'll break this formula into two parts. But let's have a quick look at the whole thing first. The tube diameter, which we'd measure or stamped on the tube, divided by the bender radius, stamped on the tube bender or from the instruction manual, times the bend angle, gives us the bend allowance. Let's first calculate the bend factor. This is basically what we multiply the angles with to work out how much extra material to put onto our tube. In this example, 10 millimeter diameter tube, 24 millimeter radius on the actual tube bender gives us a bend factor of 0.4. Keep in mind, if we change the tube size, this bend factor will change. Let's have a look at this example. Bend factor of 0.4 times the 90-degree bend on the tube, and the bend allowance is 36 millimeters. So we have to add 36 millimeters to that length to get the correct dimensions. Here we have our tube marked out. So we have the first 100 millimeters, then we add the 36 millimeter bend allowance, then the remaining 100 millimeter. What that means is that we have to cut our tube to 236 millimeters to get the correct dimensions on our bent component. Let's have a look at a little bit more complex example. Our tube size is 3/8 of an inch. We'll convert that to millimeters, which works out to approximately 9.52 millimeters. The radius on this bender is 15/16, and that works out to 23.81 millimeters radius. Therefore, the bend factor is 9.52 millimeter diameter tube divided by 23.81 radius on the bender. Rounded off, again, is 0.4 factor. As you can see, the part can get a little bit complicated So we have to work systematically. So I'm going to number the areas of the tube. I create a table and start entering the values. For example, 1 is 100 millimeters long. 2, we have a 90-degree bend. So our bend factor is 0.4 times 90 degrees. We have to add 36 millimeters. Then 3 is a straight 100. Then we arrive at 4. Once again, 0.4 bend factor times 45 degrees this time. And that works out to 18 millimeters added on. And if we continue to populate our table, we can see that we'll have to cut the overall length of the tube to 422 millimeters to get the correct dimensions after all those points have been bent. Once I've calculated all the sizes and the bend allowances, I go and then mark out my tube. Some tips: align your bend marks to the 0. Always ensure that your marks are not too wide, because these errors can add up and cause a change in dimensions. So use a very fine marking pen. Use direction marks to orientate the bends. Some parts can be complicated, especially if we're working in 3 dimensions. Mark the outside of the bend direction. This is a common method. So I keep the marking on the outside of the bend, and I can orientate myself accordingly. There may be a bit of spring back. If this does occur, add another 2 or 3 degrees of the bend until that fixes the problem. Again, this will vary from material to material, but you'll eventually get the feel for it. On complicated bends, sometimes I like to make a template out of coat hanger wire or spare wire. This way I can check my angles and use it as a template while I'm bending my tube, especially if I don't have any spare material and I can't afford any mistakes. Remember, if you do make a mistake and you reverse the bend, you could damage the structure of the metal, cause cracks or annealing or work hardening. So get it right the first time. If in doubt, chuck it out and start again. Another good tip is to always practice or test your equipment on some scrap before committing material. And don't forget, practice makes perfect. Section 2, tube fittings and preparation. Again, we'll visit the parts catalogue and identify some adapters. Make sure you don't damage the tube while clamping or holding it. For example, holding it in a vise. Use vise jaws to protect the tube. Cut the tube as square as possible and remove any burrs. Chamfer the outside and deburr the inside. We will be silver soldering, so it's very important to clean the surfaces of the mating parts, especially the tube. Tube cutters can alter the mechanical properties of the tube. Use a hacksaw to cut the tube, especially if the joints require mechanical properties. Use a hacksaw. In this example, we'll refer to the bend diagram, and it looks like this is ASTM stainless, and it's 3/8 of an inch. So we need this information, and obviously I will check the tube with a vernier to make sure we've got the right material. I know what my tube size is. Now let's go to our adapter reference chart and look for the tube weld adapters. And JIC, that's the one specified in the drawing, and looks like it's a BC series. I've downloaded the catalogue, but you can access it on pirtek.com.au. According to the catalogue, my BC series, JIC by Imperial Tube, will be located on page D57. My Pirtek product code will be BC-09-06 and 9/16-18. That's definitely a JIC. And we have a tube diameter here of 9.6. That gives me 0.1 clearance. Looking good. I'm going to need a tube nut on the other end because I'll be flaring the other end of the tube. So I go to my adapter lookup chart and I'm looking for a BAN series tube nut, which corresponds to JIC. The directory on the catalogue tells me that I'm looking for page D63 for my JIC flared nuts, obviously female. Looks like it's a BAN-09, again 916 UNF, definitely JIC. Also important to remember, you're going to need to use a sleeve. In this case, it's a BAS-06. Section 3, flaring the tubes. Before we begin, this is important, not all flaring tools are the same. For our JIC flare, we are going to require a 37-degree flaring tool. Here we have an example of a 37-degree flare and a 45-degree flare. 45-degree flares on the right, and this is usually found in air conditioning systems. It's also important that the end that we're flaring is burr-free and clean. Here's a diagram showing the configuration of the flare and the flare nut. Remember to put the flare nut on, as the other side might have a fitting and you won't be able to insert it if you flare it first. Let's have a look at this quick video and then we'll resume.
From Ridge Tool, continuing with our stainless steel theme, we're going to look at flaring. So, what's a flare? Well, a flared end is this kind of thing, okay? They can come in two angles of flare, 45 degrees as we've got here, or you can have 37.5 degree flares. Quite simply, it's just a way of jointing the pipe using the fittings. Instead of using a simple compression fitting with an olive, a flare actually uses a cone seat, and that's the idea of the flare. The flare sits onto a cone seat fitting. So they're very popular with hydraulics type applications. Even things like brake lines in vehicles often use flared ends. So we're going to form a flare. So a piece of stainless steel tube we've got here. This is 3/8 tubing. And to do it, we need a flaring tool. Come in two halves, two bits to a flaring tool. This is the rigid model 345, and it has the flaring bar and the actual flaring tool itself with the cone. And it's that bit there, if you can see inside, that actually forms the flare. So you take the flaring bar, you take your piece of tube, and the sizes along here, it's marked with all the different sizes, as you can see. So we're going from 3/16 up to 5/8. So we're on 3/8 tube, so you pick the 3/8 one, which is that one there, and you put the tube in, close the bar down, and then pick up the actual flaring bar and put it into the flaring tool. Just pinch this down, get it set right. Okay, so we've got the tube set in the flaring bar. We've used a vise just to help us here. And as you can see, as I turn the handle, down comes the cone. Just to make things easier, if it's not an issue, you can lubricate the cone. And all you simply do now is just turn that handle, and the cone is on an eccentric. So it actually sort of spins round and forms that tube end into the flaring bar to give you the flare. When you've bottomed out, you can't go any further. Okay, back it off. Open that up all the way. We'll just take him out the vise, slacken off the flaring block, take them out, open up. There you go, 45-degree flared end. So that's ready now for your cone fitting to go on there and make a joint. So that's the rigid 345 flaring tool.
Flaring review. 1. Cut the tubing, make sure the end is within 5 degrees squareness and avoid deforming the tube. As pictured, you can see that we're using soft jaws to protect the tube from being crushed or damaged. After cutting the tube, check for squareness and file flat if necessary. Once again, we've used the soft jaws to protect the tube from being damaged. Step 2. Deburr and clean the end of the tube. If you don't have a deburring tool, use a fine file or a scraper to remove any burrs. Don't forget to insert the flare nut with the thread pointing in the right direction. And the sleeve. Select the correct tube diameter from the flaring die. Insert the tube to the corresponding size location. Align and tighten the clamps to secure the tubing between the jaws and the die block. It's a good idea to clamp the flaring tool in a vise or clamp it to the bench somehow. The distance in which the tube protrudes over the surface of the die will depend on a couple of test flares or your experience with the tool. A couple of drops of oil on the die will give you a better surface finish. Wind the die down into the tube until the clutch releases or the die bottoms out. This will depend on what type of flaring tool you have. It's a good idea to keep the flaring tool secured. Here you can see that I have some vice jaws fitted to the vise and the flaring tool is held securely. Loosen and remove the press and remove the tube from the die. Check the flare, check the dimensions, and then assemble and check for leaks. A few things to remember when using flaring tools. If you're unfamiliar with the material or the flaring tool, always do a few test flares before committing your material. If you have incorrect distance protruding from the face of the die, we can have a situation where we have an over flare or an under flare. In this table here, we can see that there's tolerances, top and bottom tolerances for the flare. After I've performed my test flare, I'll take a measurement on the outside diameter of the flare. In my example of the 3/8 tube, my bottom size is 11.68 millimeters and my top size is 12.45 millimeters. We can see here at 12.20 millimeters, my flare is within tolerance. Whether we're bending a tube or flaring a tube, we need to consider the bend allowance. It's not surprising that there's a bend allowance for the flares also. It's also important to remember that we need to torque our fittings up to the correct torque setting. If we don't have a torque wrench available, we can estimate the correct torque by the number of flats that we turn the nut. In this example, the 9/16-18, which is a UNF, which just happens to be a JIC adapter, recommended torque is 24 to 28 Newton meters. If I don't have a torque wrench, I can refer to the table here, and from when the nut makes contact, 1.5 flats should approximately get me 24 to 28 Newton meters. Just a reminder, the torque table and other useful tables are available from the training reference guide and the Pirtek website.